Hi, everyone. Thank you for joining me for, first of all, a recap on the IR stuff that we did in our previous lecture, and then we're going to catch up a little bit. So what we talked about was just general types of radiation, electromagnetic energy, and then we talked about waves and how there's wavelengths and how the wavelength unit isn't particularly useful for us, and instead we use this other unit that's a wave number. Now the wave number itself is the inverse of the wavelength, and because wavelength is inversely proportional to frequency, we can say that the wave number, which is that new symbol with a line over it, we can say it's proportional to the squiggle V frequency. So what I'm trying to get at is, instead of saying wave number, I'm going to use the term frequency. Now, the frequency of different types of light or energy helps us categorize it into smaller little portions. And the part that we care about, the IR spectrum, is between 400 to 4,000 inverse centimeters. That's the unit for wave number that's appropriate for us, because we have bonds within molecules that do specific types of stretching that occur at frequencies within the IR spectrum. That's how frequently the stretching or bending is occurring. And then we talked a bit about how bond length is inversely proportional to the stretching frequency. So the longer the bond is, the slower it takes to go through cycles of expanding and contracting. So a longer bond comes out to a lower wave number or frequency. Okay? We can use one example of an OH bond, and the stretching of an OH bond occurs 10 to the 14 cycles per second. That's really, really fast. And so the frequency would be represented as inverse seconds, or it might be written as the same thing would be hertz. So you could say this would be 10 to the 14 hertz. That's the same thing as inverse seconds or cycles per second. If we were to convert that into a wavelength using the speed of light, we would get a number that's 3 times 10 to the minus 4, so we'll put that in centimeters, and that's not as nice of a number to play around with. It's not a nice number to put on the x-axis, so instead we turn this into a wave number. We do the inverse of the wavelength. Remember, it's 1 over lambda, so 1 over 3 times 10 to the minus 4 is 3,300 inverse centimeters. And this is the center of the peak that we're going to expect to find on the IR spectrum. Now, that's just the numbers. Let's get back and relate to the actual bond itself. So there's an oxygen. We're thinking of it like a spring connected to a little hydrogen. This is a pretty darn short bond relative to a carbon-hydrogen or whatever, mostly because of hydrogen bonding is a big deal. Because we have hydrogen bonding, we have a very broad peak, and broad because we have variable lengths. Now we're talking about bond length like it's a static thing, but actually because there's this expanding and contracting, a bond length is actually given as an average. And there's a lot of different variations in the hydrogen bonding, or in an OH bond due to the hydrogen bonding pattern. Some are held more tightly than others. So because of that, we get this broad peak. Otherwise we just call it a big old blob, and we're expecting that blob to be centered at about 3,300 inverse centimeters. So let's take a look at our actual spectrum and relate that to what you'll be seeing in the lab. Now within the instrument, so like all of this is going on inside a bit of a mystery box, you're going to add in your own alcohol, or not an alcohol, but your own compounds. There's different compounds you'll play with, and you'll put them in between these very expensive and delicate sodium chloride plates, and within the instrument it will emit a full spectrum of IR radiation. So these are all the different, representing all the different frequencies of light that are going to be emitted onto that sample. And then the sample itself is going to absorb specific frequencies based on whichever kinds of bonds are there. And the bond that I'm highlighting in this example is an OH bond. Now there's going to be more, obviously there's more than just the OH bond on there, but the OH one is very, very obvious. You get this big old blob, like if this was around 3,300, you get a big blob big broad peak right there, and that we would assign to the OH group, and that lets us know that we have an alcohol in our compound. So this is the main thing, is that IR spectroscopy tells us what functional groups, and if not maybe the specific functional groups, at least it'll tell us the type of bonds that are in the molecule, and that's very important. All right, so that's one. But we also have different types or other kinds of bonds within this molecule. We have CH bonds. That was messy. We have CH bonds. We have those guys here. We have methyl groups. We have CH2 groups. We have all different kinds of CH bonds that have their own specific stretching frequencies, and those end up being found around the 2900 range. So we don't see a single peak there. We see a bunch of little like sharpish type of peaks that are right next to each other, and that's the 2900 region. Now, predicting the actual number requires you to use some tables that I'm going to get to here in a second, but for right now, we're thinking relative bond length, in that a carbon-hydrogen bond is longer than an OH bond, and so that's why it has a lower stretching frequency or a lower wave number. Now, there's other types of bonds in the molecule as well. We haven't covered the CH or the OH bonds. Sorry, the CH, we have covered those. We haven't covered the carbon-carbon and the carbon-oxygen bond. There's a bunch of different carbon-carbon bonds, and the carbon-oxygen bonds also show up in kind of this messy region in between 1000 and 1500. We call this the fingerprint region. Actually, all of this, everything below 1500 is called the fingerprint region, but everywhere in between 1000 and 1500 we ignore, basically because it's really messy. This is where all of the carbon-carbon and carbon-oxygen bonds show up. They overlap, and it's really hard to distinguish between those different ones, and really what we care about are the ones that stand out, the carbon-hydrogen, and more importantly, the oxygen-hydrogen bonds. Great. Okay, so that establishes that. We can actually give another couple of examples where there are different types of carbon-hydrogen bonds, whether it's an alkene or an alkane. So, for example, if we had, let's say we had a molecule that had both of those, like we have some carbon-hydrogen bonds that are of an alkene, and then some carbon-hydrogen bonds that are of an alkane. Right? This one here, actually, I'm gonna redraw that molecule so they line up a little better. All right, that's better. So we have the alkene stuff. That's like an example of an alkene hydrogen, and then we have the alkane ones right there. So you'll notice that there's a big difference. I'm just giving you the numbers and I'm trying to figure this out. We have a difference between the stretching frequencies of an alkene and an alkane, and that has to do with, in short, the hybridization. So because you have an sp2 hybridized carbon here, this hydrogen is held more tightly. This means that it's a shorter bond, and that's why we end up with a higher stretching frequency. In the example of an alkane, these are all just single bonds, so if we're highlighting one, this is sp3 hybridized. This is a bit of a longer bond, and that's why we see a lower stretching frequency of 2900. Okay, so those are just some other examples that'll be helpful to you when you're setting stuff up. And then what we have below is a bit of a recap. We have 4 main regions of the IR spectrum, and that's defined or broken down by what types of bonds we find. So NH, OH, and CH bonds, which are some of the shortest bonds, once again have the highest stretching frequency, and that's because hydrogen is the smallest atom, so it's going to have the smallest bonds, the shortest bonds. We can see some direct comparisons finally. Carbon-nitrogen triple bond is going to be shorter than a carbon-nitrogen double bond, so it's going to have a relatively higher stretching frequency. You can see a similar comparison between carbon-carbon triple bonds and carbon-carbon double bonds. And what's not shown on here kind of on purpose is that between here, with 1000 to 1500, we see the carbon-oxygen, carbon-nitrogen and carbon-carbon single bonds all showing up. They tend to overlap. It's pretty messy. It's difficult to distinguish anything from anything else. And then finally, the last region, this is where we have CH out of plane bending. And so everything else that we've been talking about has been like, here's this CH bond, and we've been talking about it expanding and contracting, like them getting closer and farther from each other. But the out of plane bending is, it's just like it sounds, but in case it's not, you don't know what I mean by just like it sounds, it means this hydrogen is coming towards you, right? So kind of like towards you, and it's going away from you, but it's in that same, in the same plane here, meaning it's, sorry, out of that same plane. Wow, okay. So here's the plane that we're defining, and the hydrogen's coming up and down. And so that's why it's like it's all of their total region. And that, I think, is enough to just kind of summarize the different regions of the IR spectrum. To give you guys an idea of how to prepare for the lab, I at least just wanted to show you here where we left off from our last lecture. We're identifying different functional groups, and I wanted to go through and start this for carbone. We actually have a bunch of different functional groups in carbone. First of all, we have this ketone, and then we also have alkenes. And then I'm not going to circle them, but we definitely have some alkane stuff we're going to be looking out for carbon-hydrogen bonds. What I want to do is show you how you're actually going to come up with the expected wave numbers. I think it would be a great thing for you guys to try this for as many as you can over the weekend. And once again, I'm going to get you started, but I'm going to switch over to the IR table. It's posted online. I'm going to hand them out in lecture on Monday. But once again, it is kind of like near the bottom of the Chem8L website. So this is the IR table, and it's organized by functional group. You're going to be looking for the type of functional group first. It'll tell you, so here's the type of vibration and the type of functional group. It'll tell you the position where you're expected to find it. The intensity is not always so important, but sometimes it'll tell you if it's like medium to sharp. Some of them, like alcohols, for example, the BR stands for broad. And then there's just some other little notes that we actually will find useful. But I'd first like to focus on the vibration or the functional group. I think that should say functional group. Functional group. And yeah, whatever. It's organized by functional group anyway. So we said that we're looking for the alkane stuff. We had alkenes, and then we had alcohol. No, not yet. We had ketones. Okay, so this is the kind of stuff we're going to be looking at. Great. So from there, you'll notice within the alkene part to identify it that we have two options. We have the same thing for a ketone. So I wanted to find this SAT. This is defined as saturated. Versus conjugated. I'm going to give you a little intro to what saturated versus conjugated actually means. So let me go back over to the structure on the previous page to decide which ones we're going to be using. So here I just added these examples of what's considered to be a saturated ketone versus a conjugated ketone. Now the short definition, it's not a complete definition, but a short definition for something that's conjugated is when you have alternating, double, single, double bonds. And I'm going to put a dot, 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 because it actually could be more than two double bonds that alternate. It could be 3 or 4 or 5, whatever. So there's actually quite a bit of conjugation in these examples here. Now, first of all, showing you that this is a conjugated ketone because we have a double, single, and a double. Over here, this is saturated because it's just a double, and then it goes single, single, single. So there's nothing special going on there. The reason why this matters is because conjugation affects the bond length. What I'm going to do is I'm going to show resonance structures for each. We can kick these electrons up here and show that one representative resonance structure is actually when it's a carbon-oxygen single bond. All right, but the other ketone can do that as well. The difference is there's more electrons in what we call conjugation, or otherwise more electrons in resonance. So we switch these electrons over, that's negatively charged, that's a double bond, that's a positive charge. All right, and so these are two representations of when you have a carbon-oxygen single bond, and carbon-oxygen single bonds are longer than carbon-oxygen double bonds. The difference here is this is more resonance stabilized because you have the charge being shared across more atoms. So there's more space for that charge to exist. This is less stable because there's less space, and I'm referring specifically to the carbon-oxygen bond there on that molecule. What that means is this has what we call greater single bond character, and if it, or in other words, it's a longer bond, right? To kind of summarize, conjugated ketones have longer bonds, which is going to correlate to a lower stretching frequency. So let's see how that relates to the values that we had on the previous page. Check it out. We see this is a lower number because it's conjugated. These are higher numbers because they're not conjugated. So that's a little bit of a background behind those two individual numbers. And the rest of it is going to be essentially for right now copying each of the functional groups over into the table and then copying over the expected values that you're going to be looking for. So where I will leave you all is with the summary of the different functional groups that we found. And these different functional groups, out of the way. The different functional groups we found are the alkane, the ketone, the alkene, and the other alkenes. So we're going to find those alkenes 1 and 2. And just so we can be all on the same page, literally and figuratively, I'm putting the alkane first. I'm putting the ketone second. There are two different alkenes. We have the tri-substituted one first. We have the di-substituted one second. So I would love for all of you to come in with this much filled out on the table to do your best to fill out these using the IR tables. So that's going back and filling in these numbers here, that, you know, this value, the CH stretch, and then copying over those that are applicable. We already identified that there's one alkene that's conjugated, there's another alkene that's saturated, and we're going to be using the conjugated ketone example. This is for carbon. The other thing that I'll highlight, since when you get to the alkene stuff, it says see table 2 for more detail. That's why I actually had the second, or I refer you to a second table, and that's why I had the abbreviated versions, where we had a tri-substituted alkene. So we're going to be using this value here for the CH out of plane bending stuff. And then we had a di-substituted one, and that's a short version or the abbreviated version of the other double bond in carbon. So hopefully that's enough to kind of like get us started, so when we come into lecture on Monday, our memories will be jogged and we'll have a better idea of what to expect. So thank you very much. Once again, what you're expected to do for this week is actually to fill in all of this. This is part of your pre-lab notebook preparation stuff that you're going to do, and this is all going to be blank. Okay, these literature wave numbers here, there's IRs provided in a separate document. I actually show you what they should look like, and you do your best to assign those first. So there's only one column that should be blank when you come into lab on Tuesday through Thursday of next week. All right, thank you for watching. I'm actually done now. Have a good one.